All right, I think we're good. All right, cool. Here we go. Um, so I'm sitting here home. It's Thursday night, and I wanted to um, make a debrief of this ed puzzle because I was looking through the responses and I got a sense of where some of you were having some areas of confusion, some misconceptions about kind of how to understand specific heat capacity and how to understand, I guess, just some of the questions in here and how heat and temperature relate. So the purpose of this video is to help you sort of sharpen your understanding of specific heat capacity. So it's to help you understand the concept better, so that when we go into uh, the next activities following this, related to doing some calculations and really kind of diving into using this information and applying it, um, I want you to feel good about the concept before you get to that activity or those activities. So without further ado, let's jump in. I'm going to go question by question, and we'll just talk about the things that were um, kind of confusing for some of you, I think. So we'll start at the beginning, and you can jump around in this video however much you need. You don't have to watch all of it. If you understand all of this, you don't have to watch any of it. It's just meant to be beneficial in however way that makes sense. Okay, so first open-ended question: how are heat and change in temperature related? A lot of you recognize that these are actually different concepts, but related concepts. So if you can imagine a Venn diagram with like two circles and they overlap, probably seen that before. Um, Heat and temperature both have independent and unique properties, but they also have some commonalities, right? If you think of like hotness, when you touch something, heat and temperature are related to that, but temperature is a measurement of the hotness, and heat is not a representation of the hotness that is in something, like in water, but it's heat is the energy that actually transfers in or out of something. Temperature can't go in or out. Temperature doesn't go anywhere physically. Um, but something can have a temperature, right? So a couple of you were saying that like heat and temperature are really the same thing. They're not really the same thing, but they're definitely related. So next question. So what temperature will the water boil at in the glass and in the bathtub in case one? Most of you got this. If you didn't, I think it's okay. But like thinking about this, I think he said it afterwards that water is always going to boil at 100 degrees Celsius, no matter how much of it you have. And that goes back into the idea that temperature describes the amount of kinetic energy on average that particles in a system have. So if you imagine this glass of water, um, if you're averaging the amount of kinetic energy in the particles of water in there, and then you go into the bathtub and again you average the energy of the particles in there, it doesn't matter how many particles you have because we're still talking about an average, right? um, if you want to think about numbers, you could say that in the glass of water, let's say some arbitrary number, that some of the water particles have 1 unit of kinetic energy and some particles have 10 units of kinetic energy. The average might be 5. 1 and 10, average might be 5. In the bathtub, maybe you have more particles that have 1 unit of kinetic energy and more particles that have 10 units of kinetic energy. But again, if you just average, then you still end up with an average of 5. And again, these are arbitrary units. It's just for the sake of talking about this. So again, temperature, it doesn't matter how much of something you have, they can all have the same temperature. Okay, so that's why they'll both boil at the same temperature, 100 degrees Celsius. Now, which one will boil faster? I think, again, a lot of you are thinking about this in a way that makes sense. The cup is going to boil faster because you have less water that you have to add energy to get the kinetic energy of particles up to that level where the temperature or average energy represents 100 degrees Celsius. So you have to heat up fewer particles overall with the cup, and so the cup will take less time. It'll boil faster. What is one variable that affects the amount of heat needed for a temperature change? In this case, we're talking about mass, because mass is a representation of how much stuff you have, how many particles of the substance you have. So in this case, if we're talking about the water, if you have more water particles, you have more mass. And so that is a variable that affects how much heat you'll need to have a temperature change. And that gets into this question right here. Okay, this was a little bit tricky for some of you. So the big idea with this question is that if you have a starting substance, and this, we can even think about the glass and the bathtub example here. Let's say the bathtub, let's say this is a really, really tiny bathtub. So the bathtub actually has 3 times the amount of water as this, but only 3 times, right? So now let's say the water in the cup on the left needs 500 joules of energy to increase its temperature by 30 degrees Celsius. Okay, so now if our mini bathtub has a mass that is 3 times more massive than the glass of water, then you'll need 3 times the amount of energy to get all of the particles on average up to that point where the average kinetic energy is increased by 30 degrees on average. Okay. I think that I might have revised the wording in this question a little bit. So this might have been confusing for you just because of the wording. And if that's the case, I apologize. You can email me if you think that the scoring or the wording caused you to make an answer that was, like if you would make a different answer now, or if you would have made a different answer with this wording, email me and we can chat about it. But yeah, so the amount of heat to heat up 3 times the amount of water should be 3 times the amount of energy. So instead of 500 joules, we take 500 times 3, we get 1500 joules. Okay. Let's see. Which cup on the right needs more heat to raise it to the temperature he indicated? So if you're starting at the same temperature and you're raising cup B to a higher temperature, that means that the particles on average will need to be moving faster than these. And if they're going to be moving faster, then you need to give them more energy. So you need more heat. So cup B. Okay. The amount of heat required to change the temperature depends on how much you want to change the temperature. And that goes back to this example. If you want to change the temperature more, like instead of going from 20 degrees to 50 degrees, you want to go from 20 degrees to 90 degrees, that means you're going to be changing, or you're going to be increasing the amount of energy in the particles that much more. And so that's why this answer makes sense here. All right. 2 equal masses of water, the same temperature, are heated. So this is the same question, basically. It's just a different example. So if you're starting at 20 degrees Celsius, the first one reaches 50, the second one reaches 80. instead of 90. Which one receives more heat? The second one, because you have to put more heat into it to increase the energy of those particles that much more. Okay. In this case, this triangle symbol is the Greek letter. Actually, this is a letter, believe it or not. Actually, that's totally believable. But you may not know that if you don't know about other languages that are not English with Roman letters. So this is a Greek letter. It's a capital delta. And in the scientific world and the math world, we use it to represent the symbol for change. So this stands for the change in temperature. And in this case, C stands for specific heat capacity. There's a different term called heat capacity without the word specific. That's a little bit different. It's also represented with a type of C. So if you're looking online for different information about heat capacity, specific heat capacity includes a mass component, whereas just heat capacity doesn't include a mass component. So just something to think about. But this answer is specific heat capacity. I think some of you chose specific capacity, but we are talking about heat. Because in this equation, when we use the letter Q refers to heat. So the word heat should be involved. Okay. In terms of writing your own definition of specific heat capacity, a lot of you are getting the idea that a technical definition is the amount of energy required to increase the temperature in, like if you have 1 gram of a substance and you want to increase the temperature of that 1 gram of one substance by 1 degree Celsius, then the specific heat capacity is the number that represents that much energy. So to simplify things, I have a visual for you. Okay. So let's imagine, I drew this last year in class at one point. Let's say you have 1 gram of oil, like vegetable oil, and you have 1 gram of water. Okay. So let's say you have vegetable oil that has a specific heat capacity of 1.2 joules per gram per degree Celsius. And then with water, you have 4.2 joules per gram per degree Celsius. So what that means is that if you have 1 gram of water, which we have, easy numbers, then for that 1 gram of water, for every 4.2 joules of energy you add in as heat, you can increase the temperature of that water by 1 degree Celsius. So you're going to be changing the average energy of those kinetic those particles in a way that changes the temperature by 1 degree Celsius. So if you add another 4.2 joules, then that's how you can get the temperature to raise by another degree Celsius. And let's say you only had 1.6 extra joules remaining, because you're adding, in this hypothetical situation, you're only adding 10 joules of energy. Let's say you have 1.6 joules left over. That's still going to heat up the water, but not by a full degree Celsius. So the 1.6 is, about between a half and, between like maybe a quarter and a half-ish. So this is going to be less than half of a degree Celsius increase. So for 1 gram of water, this amount of energy, 10 joules of energy, will increase the water by about 2.5 degrees-ish, maybe 2.25 degrees Celsius. So for oil, though, if you have 1 gram and you're adding the same amount of energy, so let's say you hold these both over the same size flame for the same amount of time, that would be a way to have the same amount of energy. Then with the 1 gram of oil, Because oil actually increases in temperature at a faster rate, what that means is that you can have an average increase in the kinetic energy of oil particles, and that will happen with less energy input than for water. So water takes more energy to change its average. So it takes more heat to change its average kinetic energy. Whereas oil, you can add a relatively smaller amount of energy, of heat, to change the average kinetic energy of the particles by that same 1 degree. Okay, so what that means is that if you have 10 joules of energy, then because the specific heat capacity, so there's our word again, specific heat capacity, because specific heat capacity is 1.2 joules roughly for vegetable oil, let's say, that means if we break down the term specific heat capacity, that means that 1 gram of oil has a specific capacity, or has a capacity for a specific amount of heat before it will increase by 1 degree C, right? Water has a different specific capacity for heat. So you can think about it as, I think of it that way, like it has a specific capacity, a specific amount that it can take before it changes in temperature. Okay. So for oil, because the specific heat capacity is smaller, that means that it will change temperature at a faster rate. So 1.2 joules will get you 1 degree of temperature change, and then 1.2 joules gets another degree of temperature change. And so then if you just increase that 1, 2, 3, 4, 5, 6, 7, 8, with the same 10 joules, you actually get a temperature change of around 8.5 degrees, or 8 1/3 degrees. Rather than over here, you only increase the water's temperature by 2.5 degrees. So if you are confused about how heat and temperature are different, this can help you understand that again, temperature is a measure of how much energy is in the particles on average, how much kinetic energy. Okay. But the heat energy will not necessarily determine how much kinetic energy the particles exhibit, which is why the temperatures are not the same, even though you added the same amount of heat energy. Okay. So if any of that was confusing, or you want to just refresh, you're like, I think I get it, but I'm not sure, I really encourage you to go back and rewatch this section and then try and explain to yourself like what I'm saying. Try and restate this in your words. I do this all the time if I'm trying to learn something new. Like I just kind of talk to myself and like, well, how does that work? How would I explain that or that or that? And then if I can't quite get it, it means I just need to go back and keep trying. And then if I try a couple times and I'm still stuck, then maybe I'll go to office hours, right? Yeah, that's a shameless plug for office hours. I've seen some of you at office hours, and we have a great time. We get some good things done. I encourage others of you to be there. I would like you to be there. Okay, so let's finish up our ed puzzle over here. Okay, we were just looking at a definition of specific heat capacity, how to make sense of it. In this question, which substance in the chart has the lowest specific heat capacity? So in this case, we just look for the lowest number, really, because these numbers are, again, representing joules per gram per degree Celsius. So how much heat energy does it take to raise 1 gram by 1 degree Celsius? Over here, you can see that specific heat capacity can also be measured in units of calories. And when you see the word calorie, this calorie has a little c, like a lowercase c, and lowercase c calorie is related to a food calorie that you see on a nutrition label. They're not exactly the same, but they're definitely related. So it's still a unit of energy. And so here, because these are the lowest numbers for iron, iron requires the least amount of energy to change in 1 degree, for one gram of it to change 1 degree Celsius. So what that means is that iron is a pretty good conductor, right? It will change its temperature and transfer that energy relatively well. And that's often why a lot of cookware, like if you might have a cast iron pan at home, for example, this is partly why, because the pan will hold the heat well and then conduct it, transfer it to your food. So let's see. And you might have seen, historic cookware, like cookware that I think people in like, I don't know my history very well in some situations, but like if you look at, I think a lot of different civilizations, wherever there was iron in the ground, in the rocks, and the people could kind of harvest the iron. And if you had certain technology, I think different places in Europe had this technology a while ago. You could create cookware, so like cast iron cookware, like big pots, pans, tools to move food around, right? Lots of different things, all made out of iron. So in this question, 300 grams of liquid water are heated from 20 degrees C to 90 degrees C. So the key with this one is that the energy you put in is tied directly to the change in the temperature. So if you start at 20 degrees C, that means that 20 degrees C represents how much energy you currently have. Okay. I guess one way to think of this is like if we were to go to a PhET simulation and we go to the states of matter simulation, which we've seen before, look back at it. States of matter. Okay, so right now let's get to 20 degrees C. Okay, these particles of ice. Oh, that's neon. Sorry, water. Let's go to water. Okay, so we're almost there. Okay, we're at 20 degrees Celsius. So at 20 degrees Celsius, we're above freezing. This is liquid water, and the particles have energy. So if we're going to go back here and we're going to raise this to 90 degrees Celsius, then mathematically, our heat calculation needs to be based on the change in temperature, which is why in the equation, we have a delta T. Okay. We don't want to use the number 20. We don't want to use the number 90. We need to take 90 minus 20. And that will represent all of the energy I'm about to add right now to go up to 90. Oh, I landed right on 90. Sweet. So all of that heat I just added. It was so easy to add heat. I just pull up this thing. All that energy I just added is directly dependent on a 70-degree temperature increase. So 90 minus 20, because it increased by 70 degrees. Okay. Let's see. So that's why mathematically this would be 70 degrees. The specific heat capacity for liquid water is 4.18 joules per gram per degree Celsius. And since we have 300 grams, we have to scale this up. We multiply this by 300, and then multiply this by the temperature change. So that's why we have our mass times the specific heat capacity for liquid water, 4.18, times 70. And that will give us this number in joules. Okay. The specific heat capacity can be different for different substances. That is true. And we know that because these numbers are different, basically. And so again, these numbers, think back to our visual back here. When these numbers are different, it means that it requires a different amount of energy to heat up 1 gram by 1 degree Celsius. Okay. In your own words, what does it mean to say that different substances have different specific heat capacities? There's a wide range of how you all worded this, but I think the basic idea is that different substances will change their temperature. So if you have if you can keep the amount of heat that you add constant, and let's say you were to be adding the same amount of heat to each of these 4 substances, they would increase in temperature by 4 different amounts. So in other words, each of these 4 substances would experience a different temperature change for the same heat input. Same idea over here. And so some of you are saying that if substances have different specific heat capacities, then that can mean that they change in temperature at different rates. And I think that makes sense to say it that way too. Like if you look at this as a rate, the oil is going to change in temperature and increase in temperature or decrease in temperature at a faster rate than water will. So like if you were to heat up some oil to fry some oil, and then you were to heat up some water, and then you get them to the same temperature, and you have the same mass, and then you turn off the heat and let them cool down naturally, which one do you think will cool down faster? Like change in temperature faster? Probably the oil. You could test that. Test that at home. At least, and so this one, again, mass times specific heat capacity times change in temperature. Some of you chose this one. I'm not sure why. Usually if we're dividing, there's at least a division symbol. But that's okay. Sometimes you'll see equations where there's no specific multiplier sign. And so this is something that you can just get used to seeing. Like sometimes there's a little dot, sometimes there's an X to show multiplication, and sometimes there's nothing. But if there's nothing, then you can assume that we're multiplying these variables together. Okay. So that's it for the debrief. And just so you know, this is sort of leading you into an assignment that's, I think, going to be number 2.17. It's going to look something like this: snack food calorimetry wrap up. And I'm going to be having you kind of apply this idea, this understanding of specific heat capacity, by finishing up some calculations related to the chips. So what you're going to be doing is first taking a look at what chips you were testing with, if you tested. Okay, if you didn't test, you can look on Piazza and find some data from someone who did test. And if we look at these nutrition labels, we can find that 1 serving of these chips is 28 grams. So serving size is 1 ounce, which is 28 grams. It's about 13 pieces or 13 chips. But don't measure this in chips, because chips are different sizes and different masses. So if we measure in grams, then we can be consistent. So we have 150 calories, these food calories, per 28 grams. Actually, it's the same for Flamin' Hot Doritos. 150 food calories for every 28 grams. It makes you wonder, are these actually the same chemical substance? Flamin' Hot Doritos and Flamin' Hot Cheeto Puffs? Question. Maybe they are. So because these have the same numbers, this actually makes things a lot easier, especially if you're borrowing someone's data, because you don't actually need to know what type of chip they burned. All you need to know is that they have the same starting given energy density. And energy density is a measurement of how dense the chemical energy is stored in your food product. So in this case, we have 150 calories for every 28 grams. And so you can set up, I forget, I feel like this is called an inequality, but I can't remember. I forget things, then I have to like remind myself all the time. So if you forget things, don't worry. Teachers forget things too. So what I would do though is write this down where 150 is on top of 28, and then the whole thing is equal to question mark over 1 gram. So 150 calories for every 28 grams means how many calories for every 1 gram? So if you divide 28 by 28 and you get 1, what happens if you divide 150 by 28? What number of calories should be in only 1 gram? Okay. Once you figure that out, then this is your given energy density. Okay. And in these math calculations, what you're going to be doing is using this given energy density and actually calculating your experimental energy density. Okay. And what that means is that in your experimental energy density, you're going to be able to calculate the number of calories that you think came out of the chip that you burned. And then you'll be able to compare that number of calories to the mass of the chip that you burned to see how much energy was actually, how much energy supposedly came out of that chip and went into the water. Okay. And because you probably had some heat loss to the environment, like the air outside the chip in the can, the given energy density is probably going to be quite a bit different from the experimental energy density. And so in this process, I'm going to help you figure out how to calculate the percent error for this as well. Okay. And so actually, the last thing to know before we end this video, and then you can go off and do things. If you made it this far, you're a rock star. I hope this is helpful and you're going to be able to make sense of things now more so. So you should see in this Due Friday section, we're still in cycle 3, week 3. You should see that there's this snack food calorimetry wrap up. I'm going to publish it tomorrow morning, which is why you don't see it now. And then this right here. So know about this. These are my notes from class last fall. Okay. And these show you some calculations I did with the class where I'm going to just suggest that you kind of study this. And maybe I'll explain just really quickly and then you can come back. If this doesn't make sense right now, you can come back to it. But think of it this way. We can start noticing heat that has come from someplace or gone into someplace, right? J is a measurement of the energy in something. So J chip could represent the joules of energy stored in a chip. And JW is the amount of joules of energy in this water right now. Okay, so, and then Q represents heat. So if we release J chip is essentially getting converted into Q chip. Okay, so Q chip equal, so the if you have an ideal system, like if we're assuming that all of the energy that came out of the chip went into the water, then Q chip should equal QW, the amount of heat that is absorbed by the water. Okay, so when you measure the temperature change of the water, TW, and then you have the mass of the water. Okay, so if you had 100 milliliters of water, that's actually 100 grams of water. This is like the key thing to note, because 1 gram of water, 1 milliliter of water actually weighs 1 gram. So this makes it super easy for you. So MW for you should be 100 grams. So you have your change in temperature, 100 grams, and then S is, okay, and this, sometimes you'll see this written as S, but this is the specific heat capacity for water. I know earlier in the video we saw it as C. Sometimes you'll see it as S. So specific heat capacity for water. So this is the same situation that we saw in the video back here. So this equation, just change C to an S. And then you have Q equals SM delta T. Not there. Q equals SM delta T. Okay. So, yeah. So once you use this process, you can calculate how much heat was absorbed by the water, and then that heat, it only could have come from one place, or we want to say that heat came from only one place, right? We want to assume that heat came from the chip. So if we can calculate QW, we can kind of work backwards and see, okay, well, if QW, like whatever QW was, that should equal the amount of energy, the amount of heat energy that came from the chip. So that's Q chip. Okay. So now, if we know what that is, what QW is, and we know what Q chip is, we know how much energy was released from the chip. Now what we do is we say, okay, assuming we had great insulation, which you may have had great insulation, but you may not have had great insulation. What we say is the energy density of the chip is however much energy was stored in there. So we get J chip by finding Q chip. So J chip is, in this case, going to equal Q chip. Just like QW is going to equal JW. It's sort of like J, in this case, the J variable is like describing like a bank account value. Like the measurement, like the actual amount in the bank account. How much energy is in the substance when you measure it. But Q is measuring the transfer. So Q is like how much cash you take out of your account, or how much cash you put into your account, right? So even though they represent the same amounts, Q chip and J chip, we use different variables just to represent that one measurement is like a stored energy, and one measurement is a transferred energy. Okay. So when you take the mass of your chip, so G chip, you could also say M chip, I guess, like delta M. I don't know why I wrote G here. It would make more sense to say M, like M chip. So think of this as like J chip over M chip. So the amount of energy that was absorbed by the water should represent the amount of energy released from the chip. And then if you take that value and divide it by the number of grams in your chip, which is probably between 1 and 2.5, then you can find out what the supposed energy density is of your chip according to your experimental data. Okay, so that's when you say, okay, well, let's say we measured that in this case, let's say we do a little bit of math. I'll walk you through this. Let's say the temperature change of the water right here, was 45 degrees. So it increased by 45 degrees Celsius. The mass of the water, let's say it was 30. The specific heat capacity of water is 4.2 joules per gram per degree Celsius. We multiply these together. And then the amount of energy absorbed by the water is this number, 5670, which means that that's also the amount of energy that was supposedly stored in the chip. And so then we take that value, divide it by the mass of the chip, which in this case was 2 grams. And this tells us that the energy density of our chip is 2835, so 2,835 joules per gram of chip. But this assumes that there was no heat loss. Okay. You might be looking over here and wondering what these diagrams are. You don't really have to worry about these right now because last year when we did this experiment in the lab, everyone was able to measure the mass of their chip at the end of burning it so that you can find the mass, the initial mass, and the final mass. And then find the difference. And the difference would represent the amount of chip that actually burned, right? Because maybe if there's an unburnt section of chip, maybe that represents chemical energy that's still there. So you wouldn't want to count that. We don't have the ability to measure the final mass of the chip, so we're just going to assume that the whole chip burned, and we're going to accept some error. Okay. So this is how you would find the experimental energy density. And then this is the value that you would compare back to your given energy density based on the nutrition label in the chip or on the chip bag. Okay. And so then how do you do that comparison process? So that's what percent error is for, or calculating percent error. So I encourage you to look at this set of notes, and you might have seen percent error calculations before, but the goal of percent error is to think about what is the difference between your experimental value and your ideal or your given value, right? So here's an example. Pretend you work at Jamba Juice. You make smoothies. You are told by your manager to make 30 smoothies per day, but you only make 220 smoothies per day. So what's your percent error, right? What's more meaningful? So what you want to do is find the difference between those numbers, first of all. Okay. And so that's why we use absolute value mathematically. You can say 220 minus 300 or 300 minus 220, and then absolute value, take the absolute value, and your number in the numerator here will always be positive. So it doesn't really matter which way you subtract. What really matters then is which of these numbers you put in the denominator. So when you're finding the difference between these, so you're finding like how off were you? If you needed to make 300 smoothies, how much didn't you make? Right? You made 80. That's going to be a number that your manager's going to want to know, right? But then what do you compare that number to? Do you compare that number to how many smoothies you actually made? Or do you compare that number to how many smoothies you were supposed to make? Right? In the end, B is going to make more sense. It makes more sense for your manager to compare how many smoothies you didn't make, to compare that number to how many smoothies you were supposed to make. Because then the manager is able to see, okay, if 300 represents all that they were supposed to make, if that represents 100% of what they were supposed to make in this pie chart, then in that case, 80 represents this fraction of that whole number, that 300 whole number. Okay. 220 does not represent the total number you were supposed to make. So it doesn't really make sense mathematically to compare 80 to that number. So I put these both here for comparison. A doesn't make sense. So you don't want to put the experimental number, essentially, you don't want to put that in the denominator. You want to put the given number or the ideal number in the denominator. And then when you divide your difference by the intended value, then you get a fraction, and then you multiply that by 100, and you can get that fraction as a percentage. So what we would say in this case, actually, this number is wrong. That should say 27%. Because this should say 0.27 times 100. So that should be 27%. So that means that if you worked at Jamba Juice and you didn't make 80 smoothies, that means that you didn't make 27% of the smoothies that you were supposed to make. Again, that's why what you were supposed to make should be part of your equation, your formula here. Okay, so how does this relate to the snack food calculations? Right, so once you have your experimental energy density of your chip, you take this number, and that essentially takes the place of this experimental smoothie number. This 300 number, this is going to be the number you get from the chip bag when you are finding how much energy is stored in 1 gram of chip. So this is the comparison that you're doing. And then when you do this, you say, okay, energy density of a Dorito according to the chip bag. Energy density of the Dorito according to my calculations. Find the absolute value. And then divide that whole thing, that difference, by the energy density according to the chip bag, once again. And that will tell you how much was my experimental number off or different from what the bag said I was supposed to get. And that will help you figure out how much energy was lost. That will help you figure out, okay, maybe we lost 27% of our energy. That's a huge amount of energy. It's a huge amount of energy, right? Like, what if your parents could save 27% off of their gas bill instead of spending 40 or 50 or 60 or more dollars to fill up the tank of gas? They could save $20 every time they go to the tank, and then $20 every time. That adds up, right? Get some new shoes with that. Get some new food, whatever. So there's other images here, and like this one, and then this one right here. These represent the same calculation process. I just did the explanation process like a whole bunch of different times in my different chemistry classes last year. So you can ignore the other pages if you understand the process, or you can look at them and try and make sense of them. Now that hopefully this is making a little bit more sense based on how we talked through it here. Okay. So let's see, there's one more thing to do. And that is calculation between calories and joules. Okay. So one thing that you might see is this idea that there are food calories and other things called small calories, or small calories and large calories. Okay. I don't know who came up with the idea that there should be 2 different types of calories, and the only difference is that one has a capital C and one has a lowercase c. So the big idea is that, so the small calorie is also called a gram calorie. And you'll notice that 1 gram calorie is equal to 4.184 joules. And where did we see that number before? 4.18. Oh, yeah, right back in the Ed puzzle. Okay. So if we look here, the specific heat capacity for liquid water is 4.18 joules. If we look at this number in gram calories, or small calories, lowercase c, the specific heat capacity for water is 1 calorie, 1 gram calorie, 1 small calorie per gram per degree Celsius. And this is a reflection of the fact that 1 joule is just defined as 4.18 times bigger or more significant than 1 food or 1 gram calorie. Okay. And so looking back here, right, 1 small calorie is the same as 4.18 joules. And there's a thing, so a food calorie with a capital C, which is what you see on a nutrition label, the scientific name for that is a kilocalorie. Okay. And a kilocalorie, you'll notice this is like the same number we just saw. This used to be 4.184. Now it's 4.184. So this number is the other number multiplied by 1,000. Right? 4.184 times 1,000. 1,000 has 3 zeros in it. So you move the decimal 1, 2, 3. And then you get this. Boom. So now, what this means is that 1 kilocalorie or 1 food calorie is equal to this many joules. Okay, and the reason why this is important is because when you are going to do your percent error calculations, you have to make sure that you're using the same units. Okay, so if you are calculating energy density, your experimental energy density, you're probably going to be measuring it in joules. Okay, you may not. It all depends on which specific heat capacity value you use. So you can use a specific heat capacity value in joules. You can say 4.18 joules per gram per degree Celsius, right? And then you get your Q value, and the unit for your Q value would be in joules. You could also do this calculation using this other version of the specific heat capacity, okay? This number still represents the same properties of water and how much energy it takes to change the temperature of the substance per gram. But we're just measuring energy in a different sized unit, basically. A gram calorie here is a different sized unit than a joule, but they both represent energy. So what may be easier, if you're looking to streamline this process, it may be easier for you to do your energy calculation, and maybe like to calculate your experimental energy density using the calorie version of specific heat capacity. Because then you don't have to convert later. Because what's going to happen is that when you have your experimental energy density, you're going to need to compare this, or you need to put it in a formula like this. And since you're comparing experimental energy density to, or this is experimental, you're comparing that to your known energy density, which is from the chip bag. The chip bag is measured in kilocalories or food calories. So you need to make sure that when you are putting both energy densities in your formula here, that they have the same units. So they either both need to be in kilocalories or both need to be in gram calories. I guess you could convert the the value from the bag into joules, you can do that too. And then they're both in joules. Either any of those ways is fine. But so like if you were to, let's see, if you were to use this value, like water requires 1 gram calorie to raise in 1 degree, for 1 gram to raise by 1 degree Celsius, you would need to divide this number by 1,000. So 0.001, I think. 1, 2, 3. Yeah, 0.001. So that would say 0.001 food calories to raise 1 gram of liquid water by 1 degree Celsius. If you were to use that number when you're doing these calculations right here, then you already have your experimental energy density in food calorie or kilocalorie units. And then it'd be easy to compare to the bag, to the value that you get from the bag, your known energy density. Okay. But this is the whole shebang. I think I've said everything that is part of this. And I know that is a lot. This video is way longer than I thought it was going to be when I set out to make it. But hopefully you see that this is really comprehensive. There's a lot to this, right? So we started by looking at what specific heat capacity really means conceptually, and then looking at how we work with that number mathematically, or how we work with that concept mathematically. And then once we think about it mathematically, and then we looked at it conceptually as well with a little bit of modeling. Then, now we're looking at how do you take that conceptual information and start visualizing it and applying it to a visual that now you've been working with a little bit, right? If you get to do the experiment outside or maybe inside, or if you just, you know what to do, but you just didn't actually collect the data. Now we're applying that concept to this mathematical work. And then once you are able to figure out what your percent error is, again, this is going to tell you how much waste heat you created. And knowing how much waste heat you made, or what percentage of heat was wasted or lost, this is what we're going to use going into our final week of class next week. Okay. And this type of calculation is going to relate to some of the things I'm hoping to have you do next week, which I hope should be interesting. Okay. So with that, I'm going to end here. At this point, there's probably things that you could go back to and revisit to strengthen something that you think you know, right? You might have already known how to do all of this. And so you watch this and you're like, okay, I'm good. But I'm guessing that that's the minority of you. So I'm guessing that for a bunch of you, you watch through this and you're like, oh yeah, that makes sense. I see how that would work, right? But like with a lot of things, when you see something once, it might not quite sink in. It might not stick with you. Okay, so you may just want to go back in the video, like click back to sections of the video that you think might be helpful, or more helpful than others, or less helpful than others. Okay, and just like jump around, because again, like you saw in the video, if you're still with me on this, you saw that I jumped around whenever it made sense to compare one website to another. Okay, so anyway, there's a lot of information in here. I hope this is helpful, and I look forward to going on more of a heat transfer journey with you in the following week. And remember to come to office hours if you want to chat about any of this. I'll be there. Yeah, I'll be there. The office hour timing for whenever you're watching this video should be in Canvas on the agenda page. So I'll see you if you come in whenever that time says. All right. Again, hope that was helpful. Talk to you guys later.